So have you ever really wondered what it takes to build a professional AI product? I mean, it's not just about some clever algorithm, right? It's a full-on engineering process. Today, we're going to pull back the curtain on the actual blueprint for building AI. Let's dive in.
Okay, think about this for a second. You swipe your credit card and boom, in less than a second, a decision is made. Is this transaction okay or should it be blocked? Behind that instant decision, there's a machine learning model working its magic. So how do we get from a simple ideal like, hey, let's stop fraud, to a system that can do this reliably millions of times a day? Well, that's the journey we're going to explore right now. Pretty much every professional machine learning project follows a predictable path. We can break it down into these 5 distinct phases. This is our roadmap for today. We'll start with the design, then engineer the data, develop the model, deploy it into the real world, and finally, monitor it for the long haul. So let's start at the very beginning. First up, phase 1. This is all about planning. Before anyone writes a single line of code, you absolutely need a solid blueprint. This is where we figure out what we're actually building, and more importantly, why. Trust me, rushing this step is a recipe for total disaster. It all kicks off with something called problem framing. See, a business leader might come in and say, we need to stop fraud, which is a great goal, but a machine can't really do anything with that. So our job is to translate that vague business goal into a super precise machine learning task. In our case, stop fraud becomes a binary classification problem. For every single transaction, the machine has to answer a simple question. Is it fraud or is it normal? Now, before we go any further, the architect has to ask a really critical question. What happens when our model messes up? Because it will, and it can fail in 2 ways. On the one hand, it could block a totally legitimate transaction, which really annoys a good customer. On the other hand, it could let a fraudulent one slip through, costing the company real money. Deciding which of those errors is worse is a huge deal. It shapes everything that comes next. Okay, with our plan in place, we move on to phase 2, building the foundation. And let me tell you, this is where the real work happens. This isn't the glamorous part you see in the movies, but it is without a doubt the most important part of the entire life cycle. This slide right here, it shatters one of the biggest myths about AI. Most people think it's all about fancy algorithms and model tuning. But the reality, a staggering 60 to 80%, yeah, you heard that right, of the entire project's time and resources are spent right here, on data engineering. Getting the data clean, organized, and ready, that is the true heavy lifting of machine learning. So how do we even get all this data? Well, there are 2 main ways. For things that aren't super time sensitive, like a daily report, we use batch processing. We basically just collect data over a period and then process it all in one big chunk. But for our fraud detector, we need answers now. And that requires streaming processing, where we're analyzing data the instant it arrives, in real time. So once we have the raw data, we have to make it useful. This is a really creative step called feature engineering. A model might not know what to do with a raw timestamp like 2:37 a.m., right? But it can easily learn from a simpler feature that we create, like a simple true or false for is_nighttime. We're basically acting like translators, crafting better signals to help the machine spot the patterns. All right, our data's prepped, it's clean, it's ready to go. Now we've reached the phase that everyone thinks of when they hear the word AI. This is the science part where we actually teach the machine how to make predictions. This phase has 4 main activities. First, we have to select our algorithm. Will a simple model like a random forest do the job, or do we need the big guns, like a complex deep learning network? Then we train it by feeding it all of our historical data. After that, we fine-tune its internal settings. Think of them like little knobs and dials to squeeze out even better performance. And finally, the moment of truth. We evaluate it on data it has never seen before. That's the only way to know if it actually learns something useful.
And here's another critical question from our architect, a real reality check. It is so tempting to just grab the most powerful, complex tool off the shelf, like deep learning. But a good architect always starts with a simple baseline model first. You only add that complexity if it gives you a significant boost in performance. A lot of the time, a simpler model is just better. It's faster, cheaper, and way easier to maintain.
So we have a trained model, it works great on our laptop, fantastic, but right now it's just a science experiment. This next phase is a pure engineering challenge. How do we launch this thing so it can handle millions of real-world requests 24/7 without breaking a sweat? Just like with getting data, there are 2 main ways to serve a model. For our fraud problem, we need what's called real-time inference. The model is wrapped in an API, it's always on, and it has to reply in milliseconds. This is super fast, but it's also expensive. The alternative is batch inference, where we run the model overnight to score a giant pile of data. It's much, much cheaper, but you have to wait for your answers. You never, ever just flip a switch and turn a new model on for everyone. That is way too risky. Instead, we use a much safer strategy called a canary deployment. We start by sending just a tiny fraction of our traffic, maybe 10%, to the new model. Then we watch it like a hawk. If everything looks stable, we slowly ramp up the traffic until, eventually, it's handling 100%. This is all about limiting the blast radius if something unexpected goes wrong. Okay, the model is launched, it's working in production. So, we're done, right? Absolutely not. We are now entering the final and probably the most overlooked phase of all, the long game. See, a model's job is never really finished because the world it lives in is always, always changing. Over time, pretty much all models suffer from something called model drift. You might even hear people call it model rot. Basically, the patterns the model learned during training start to get stale and outdated. For our example, maybe new types of fraud pop up that the model has never seen before, and so its accuracy slowly starts to degrade. This is exactly why monitoring isn't some optional nice-to-have. It's completely essential. And this brings us to the architect's final and maybe most important operational question. We can't just cross our fingers and hope the model keeps working forever. We need a system that will scream at us the moment it stops working well. This means setting up automated alerts for when performance drops or when the data itself starts to look weird. And it also means building pipelines to automatically retrain the model on fresh data whenever that drift is detected. So, we've walked through the entire life cycle, from a simple idea all the way to a live production system. Let's put it all together now into a really practical takeaway, a kind of cheat sheet that shows how the tools and the complexity grow as a project gets bigger. Think of this table as your guide. If you're building a small proof of concept, you can totally get by with simpler tools, like pandas for your data, scikit-learn for development, and maybe a basic Flask app for deployment. But the moment you move to a true enterprise scale with massive amounts of data, the whole toolkit changes. You need distributed systems like PySpark and Kafka. You need powerful deployment platforms like Kubernetes, and you absolutely need sophisticated monitoring tools just to keep it all running. And that, really, is the heart of modern AI development. Building a smart model is just the first step. The real, ongoing challenge is building a system that makes sure the model stays smart, that it can adapt and evolve as the world around it does the exact same thing. That, right there, is the difference between a cool science project and a real-world, valuable product.